Okay, we're going to go over the open book test, Unit 3.7 to 3.9 of Calculus. We have learned in the last few sections about maximizing and minimizing. We learned that if we had a curve, if the first derivative is positive, it's increasing. If the first derivative is negative, it's decreasing. If it goes from increasing to decreasing at a critical number, then that's a relative maximum at that critical number. And if we found the second derivative at that critical number, if the second derivative is negative, that means it's going to be concave down, and that means there's going to be a relative maximum there. So we can use our first and second derivative tests to determine whether there's a maximum or minimum. And so we can apply this to word problems as the one we're fixing to look at. It says find two positive numbers that satisfy the given requirements. It says that the product is 192. So we're just going to assign variables to them. We're just going to call one of them the first number, and we'll call that x, and we're going to call the second one the second number, and we'll call the second number y. It says that their product is 192, which means that x times y is 192. And then it says the sum is a minimum. Now, we want to focus on the sum is minimum. That's what we're trying to minimize, the sum. But it says the sum of the first number and 3 times the second number. So I'm going to write it in green. Sum is, and we're wanting to minimize that. And the sum is expressed as the first number x plus the 3 times the second number y. Now, we know as we look at this second equation that we cannot work with that equation when there's 3 variables like s and x and y. If we could express x in terms of one of those, then we could either think about maximizing or minimizing in relationship to x. So if we would like to have only x or have only y, then we could have a relationship between s and that one that we choose and then solve. So if we come over here to the first equation and isolate the x, that means we would want to get the y off, then we would divide both sides by y, and we would have that x is equal to 192 over y. We can take that and put it in place of the x in the first equation, and we would have that s is 192 over y plus 3y. So that gives us the sum in relationship to y. And we want to look for a relative minimum in that situation. Now, if we're going to look for a relative minimum, then what do we need to do? Find the first derivative and the critical numbers. And then we want to test those critical numbers at the second derivative, right? Okay, so we're going to rewrite this. I'll just rewrite it here as 192y to the negative 1 plus 3y. We're going to write it exponentially. And then we will take the first derivative. And the first derivative would be negative 192 y to the negative 2 plus 3, which is going to look like negative 192 over y squared, and then a big old plus 3. Let's go ahead and take the second derivative. If we take the second derivative, then we're going to have 384 y to the negative 3, 3, 3 to the negative 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 3 384 over y cubed. Okay? Now, we want to find the critical numbers, right? So we need to find where the first derivative is 0 or undefined. And where would it be 0 or undefined? At y equals 0. At y equals 0, the first derivative would be undefined. So we have a critical number, and that's going to be our only one at 0. So what can we do at that critical number, y equals 0? We can plug it into the second derivative, and when we plug that in, we get undefined. We realize that's kind of a weird situation, okay? And so, as we put that 0, you can follow this little trail. We said, okay, if we let that y be 0 down there, it would create an undefined situation, and then if we put that 0 in there, we get an undefined situation. It's kind of like we dead-ended. What we should have done is said, okay, let's just let the first derivative be 0. So let's just let s prime be 0. If we do that, we would have 0 is equal to negative 192 over y squared plus 3. And then let's solve for that and see what happens. Let's just subtract 3 from both sides. Subtract 3 from both sides. I need to make some writing room here. I'm just going to kind of open up the top of the board. And so we would have negative 3 is equal to negative 192 over y squared. I'm going to put that over 1 and make a proportion out of it. So now I'm going to cross multiply. So I'm going to have negative 3y squared is equal to negative 192. Divide both sides by negative 3. We're going to have y squared is equal to 64. This looks a little better, doesn't it? So just saying, oh, if I put a 0 down there, it's undefined, so that creates undefined. We should say, no, let's let the first derivative be 0 and see what happens. So we take the square root, and we get y is equal to plus or minus 8. Y equal plus or minus 8. So we have critical numbers at positive 8 or at negative 8. Now, we could think about the negative 8, and it might possibly be a solution, but the product of the two numbers is a positive 192. So we think, well, if that's a positive answer, then we're probably going to be using the positive value. So let's test it first as we look at that. So what we're going to do then is we're going to look at that y equal positive 8, that critical number of y equal positive 8, and we're going to put it into the second derivative. And remember, we're just looking for positiveness or negativeness, right? If we have that, then we would have positive 384 over 8 cubed, which is going to be a positive, and a positive divided by a positive is positive. That means in the second derivative it's positive. What does that tell you? That means it's concave up at that point. And if it's concave up at that critical point, then what must be happening there? There must be a relative minimum, which is what we were trying to do. We were trying to minimize. So y equal 8 is a value that would minimize the sum. Y equal 8 is a value that would minimize the sum. Now we know that x times y was 192. So if we take 192 and divide it by 8, we would get the x that goes with it, right? So what's 192 divided by 8? 24. So my two numbers are x equal 24 and y equal 8. And so the minimum sum that you could come up with two numbers whose product is 192 is 8 and 24. There are other numbers who have a product of 192, but that's the only pair whose product is 192 where you can take the sum of the first plus 3 times the second and have a minimum value for the sum of those two things. But still we got that. Okay, let's look at number 2. It says find the length and width of a rectangle that has the given perimeter and a maximum area. Now, you may have studied enough to know that that's probably going to be a square, right? If we're going to maximize area, then it's a rectangle. It's probably going to turn into a square. But let's watch what happens as we try to solve this. It says the perimeter is 100 meters. Now, we're talking about length and width, and so we'll just call length L, and we'll call width W. And what's the formula for perimeter of a rectangle?
2L.
So we're going to have 2L plus 2W is 100. And we're trying to maximize or minimize what? Area. Well, what's the area formula?
Length times width.
Length times width. And so, area, which is length times width, needs to be a maximum. We want to maximize the area. Now, again, in the green with the maximum, we got 3 variables, and we need to get it in terms of one variable, right? Only length or width. So let's just isolate the L. If we isolate the L, we would subtract 2W. That would give us 2L is equal to 100 minus 2W. Divide by 2. We would have L is equal to 50 minus W. We distribute the 2. We can put that in place of L. That'll give us area is equal to length, which is 50 minus W times W. We need to distribute the W. We're going to have area is 50W minus W squared. So we have the area written in terms of the width, and we want to maximize area. Okay? Let's see what we got there. So to do that, we want to find the first derivative and then the second derivative. So the first derivative would be A prime is 50 minus 2W, right? And the second derivative would be negative 2. Now, the second derivative is a constant, and that might be boggling your mind, but it shouldn't matter. It means that at the critical number, at the critical number in the first derivative, whatever that critical number is, the second derivative is going to be negative. This entire thing is concave down. The entire curve, what that tells me is that the second derivative is negative, so our entire curve is concave down. So at the critical number, it's going to be concave down. We just need to find the critical number in the first derivative. We already know that it's going to be a maximum. So we want to set the first derivative equal to 0. We're going to put a 0, and it's good to just go ahead and plug it in and solve, as we saw in the last example. So we're going to just set it equal to 0 and solve. So we got 50 minus 2w. We want to subtract 50. And so we're going to have negative 50 is equal to 2w. Negative 50 equal negative 2w. Divide by negative 2. And we get that w is equal to 25. Now that's my critical number. And if we were to try to plug the 25 into the second derivative, well, the second derivative is constantly a negative, so that means at that critical number, 25, it's definitely going to be a maximum because the whole thing is concave down. So we can maximize the area with the width of 25. Now, if we want to know what the length would be, that would go with that width of 25, we can plug it in right here where we've got L equal. So we would have that the length is 50 minus the width 25, which is 25. Which verified what we knew before, that if we want to maximize the area of a rectangle, then we make it a square. Any questions on question number 2? Okay. All right. Now what I'm going to do is just stop there because that's really the first section. We got 3.7, 3.8, 3.9, and so that was the 3.7 portion of this. We're going to stop there and let you work on that, and then we'll do a second video for the 3.8 portion. Thank you.